So today's topic is about the growth rate, and we are comparing these three functions. So f of x is a linear function, g of x is a quadratic function, and h of x is exponential function with a pretty small exponent. Which one grows faster? Now that word itself is a little oxymoron because they all approach infinity, right? So we're comparing infinities. Have you heard that not all infinities are created equally? These are three different types of infinity. So which infinity is a bigger infinity? I mean, that's like, they're not even real as an expression. What do you mean which infinity is a bigger infinity? So there is a specific definition of what we mean by growth rate. Okay. So where I have a little graphic, Desmos graphics. Have you heard that expression that exponential functions grow fastest? Have you heard this story about the 1 grain of rice, the next day 2 grains of rice? Why don't I tell you that story? This is a kind of famous story in Asia. There is this general. Under the foreign invasion, these generals, and each country has a different variations, but this is Korean version. So Korea got invaded a lot by China, like approximately about 900 times in its few thousand years of history. I mean, it's like almost 5,000 years, so it's like 900 times. Yeah, that sounds about right. That was in my history book, at least. And then under this one invasion, this general uses the brilliant strategies and tactics and saves the kingdom. So the king is so grateful. Wow, I owe you everything, right? I mean, I'm willing to share half of my kingdom. I give you half of my kingdom. As long as you just keep pledging your loyalty to me, we can just rule this kingdom together, because without you, there wouldn't be this kingdom, right? The general says, "No, your majesty, I don't need half of your kingdom, but I have one simple request." Oh, anything, right? Today, I would like to get 1 grain of rice. Tomorrow, 2. Day after tomorrow, 4. And after that, 8. So this is an exponential function. But we're talking about a little grain of rice here, right? Okay, yeah, that's it. Oh my God, it's granted. Okay, you can have all the rice you want. Within the less than 1 month, there wasn't enough rice in that kingdom. Right, you guys can punch that 2 to the, let's say, 30 on your calculator and see how big that number is. And we're talking about grains of rice, but that's a huge number. You know what I'm saying? So then a month later, the king said, "Are you sure you don't want the half of the kingdom? Because we are going bankrupt here." Right, so it explains how fast the exponential functions grow. So we get a feeling this might be the winner here. But how do we even define these things? Because we're still comparing infinities here. I mean, that concept itself is a little weird, okay? So let's look at this Desmos. I have Desmos presentation ready. I'm gonna put them right here, okay? So 3 functions, f, linear, so horse race. I'm gonna name this one linear, this one quaddy, and this one xp, okay? And this is the starting line, and then bang, xp kind of cheated starting at 1, but hey, this is a race through eternity, so that doesn't matter. Okay, linear is soaring, right? Like on that same line, linear is already at 10 when x is equal to 1, and then xp is down here, and quaddy is like, right? Okay, let's see, let's start zooming. Oh, quaddy takes linear right there. You know what I'm saying? Okay, so linear is out, right? So quaddy is doing really well. Okay, let's see. And looks like quaddy is the winner, right? Because look at what xp is doing, flat, right? No, but this is race towards the infinity, eternity. So let's see, we'll keep zooming. And then here, xp overtakes linear, right? Okay, this is anybody race now, and then right there. This is where XP overtakes everybody and then just soars to the finish. Right, so this is the demonstration on how fast exponential functions grow. So it's a type of function that we are looking at, right? They're all infinity. So here's one little thing. This is how you define definition. The growth rate comparison. Limit, and you take two functions, okay? For example, let's say g of x over h of x. We're not going to even do, right? These two. Okay, as x approaching infinity. And then we evaluate this limit. If this thing approaches 0, then h of x wins. The denominator grows faster. If this whole thing limit approaches infinity, then g wins. You know what I'm saying? If it, okay, so we'll just do that much and then we'll reason together. So we'll say limit of x approaching infinity of, we have x squared, right? And then we have 1.2 to the x. So far so good? Okay, well, this is infinity over infinity, isn't it? So we should L'Hospitalize it. Ain't that nice? But do you guys remember how to differentiate this exponential function whose space is not e? Let's review, okay? Do you remember giant e? Followed by ln? And then I can put 1.2 to the x power here. You with me? However, with this x can go to the front, right? Like that. Now we can differentiate it. Get it? So, L'Hospitalizing it here. So limit x approaching infinity of 2x over, this is still e to the x ln 1.2. I'm going to zoom in a little bit. And then times ln 1.2, chain rule, eh? Say yes. This is still infinity over infinity. So x approaching infinity of, L'Hospitalizing it yet again. So we have e to the x ln 1.2 times ln 1.2 squared. How about that? Good. Now we can check. This is 2 over infinity, isn't it? So answer here is 0. And what is the conclusion here? Therefore, h of x grows faster. You know what I'm saying? And that makes perfect sense. If what we get is an infinity, then the g of x grows faster. But we have seen through the graphics in the horse race, xp wins, right? And this confirms it. Now, then the question is, what happens if you get something like this? Limit of 2x squared over x squared as x approaching infinity. That's 2. How do we define this? Well, 2x squared technically grows faster, right? In fact, it's twice as far, right? 2x squared is always twice x because x squared. Do we say then 2x squared grows faster here? No, we don't. For our purpose, this is the same rate. Now, you might wonder why. I mean, it's like some mathematicians say it's just a definition, but all definitions have motivation. So what is the motivation for that kind of definition, right? It's coming later. It's still same, in a way, what they are saying is the same kind of infinity. It's the same classes of infinity. It's not like in our Desmos presentation, it's not like this gap is gonna get so much farther, right? It'll be always be 2-to-1 ratio. It's the same type of infinity. And that makes a big, big difference, because later what we are talking about is when we compare the infinite area. And what we want to know is whether that, say I'm going to throw it. Okay. Say if we have some kind of function here, f of x is equal to 1 over x. And then let's say you want to find that area. That's coming up in the next section. So it's a little bit of preview. And is that infinity or is it not? Is it a finite number or is it an infinity all the way going to the infinity? Now, and then I'm gonna put another function, which is g of x. G of x is equal to 2 over x. So it's 2 times big, right? And then I want to figure out whether these integrals, this area right there, is given by 1 to infinity of 1 over x dx. Is it finite number or is it infinity is the question. Now, what we want to do is this. This is where the growth rate matters a lot. If this is infinity, then this is infinity. But let's say if this is a finite number, then this will be a finite number. It's the same kind. You know what I'm saying? Suppose this thing turns out to be 10. It's not, but suppose this integral turns out to be 10, then this will be 20. You get it? It ain't infinity, that's what matters. So this is known as the convergence of the integral. You remember convergence of the infinite series? It's that kind of idea. So what we care about is whether the thing converges or not. So for our purpose, we consider these two as the same rate. You get it? Because if one's finite number, the other one is 2 times the finite number, but still finite number nevertheless. So even if we don't get 1, if we get 1, that would be nice. But even if we don't get 1, that's still finite number, so we consider that as the same rate. It's the same classes of infinity, if you will. Good? Questions? Okay, I'm gonna start.
Do you mean even if you don't get 0?
Oh, if you get 0, then denominator grows faster. So we are getting, oh yeah, any finite number other than 0, right? Because in this case, we got 0, that means h grows faster. But if you get any non-zero finite number, then they are the same rate. Even if that number is pretty tiny or pretty big, doesn't matter. They are the same classes of infinity.